Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning in. We look at what you need to know for the test upcoming on probability and statistics. So firstly, look at statistics. So you might get a random set of data like this, and you won't need to calculate mean, median, mode and all that by hand, but you need to use Excel to do it. So if I wanted to get Excel to calculate the mean, median, mode and all that of the data here, I would put it into an Excel column, and then what I would do is in a cell, a random cell, I just write equals average. So I write this in exactly as you see it, and then a bracket will come up. You highlight all the data, all the numbers, all of these numbers, and then close bracket, press enter, and Excel will calculate the mean for you. If you want to do the median, similarly, you write equals median. You have to write the equal sign whenever you're putting a formula into Excel. You want Excel to calculate something. And then again, you highlight all of these numbers, press enter, and Excel will calculate it for you. It's the same with the mode. Now for the range, there is no function in Excel, at least the Excel version that I have. But what you can do is you can program Excel to find the max of the data. So again, write equals max, highlight the data, press enter. Equals min, highlight the data, and then press enter. And then of course you can program Excel to find the range. So you just write equals whatever cell this is in. It might be in, say, cell B20, and this might be in cell B21. You would just write something like that, and that would tell you what the range is. So make sure you can do that using Excel. You can even pause the video now and make sure you get the same answers that I get. So if I were to calculate this by hand or by Excel, the average of the 5 numbers is 10.4, so that's the mean, of course. The median would be the third smallest number because there are 5 data points, so that's 9. The mode is obviously 8, maximum 15, minimum's 8, and then the range is 7. So why don't you make sure you can get Excel to come up with those numbers. Now in this data set, we see very clearly that the mean or the average is greater than the median. So if the mean is greater than the median, we say that the data is positively skewed. So there are similar rules for the other two definitions. So if the mean is less than the median, we say the data is negatively skewed, and if the mean equals the median, we say that it is symmetrical. Now I want to point out, in case there are any purists out there, this isn't the proper definition of skewness. We're just using it as like a rough guide as to whether data is positively or negatively skewed, and if it's neither positively nor negatively skewed, it must be symmetrical. So there are other ways to determine skewness without calculating the mean or the median, and we can do that just by looking at a histogram or a stem and leaf plot. So I'm going to show you that now. Please pause and copy this down if you need. Okay, so I've just drawn a very, very rough sketch of 2 histograms. So because they're histograms, frequency is always on the vertical axis, meaning that the higher the bar is, the more frequent that score was, and score goes along the x-axis. So because it's along the x-axis and this is numerical data, there is an order to the data. So as you go to the right, the scores are getting larger. So you can see in the first histogram, as the scores are getting larger, they're becoming less frequent. In other words, there is a higher frequency of scores closer to the minimum. It doesn't matter what this minimum here is. It might not be 0 because we don't have to start at 0. But there are more scores, a higher frequency of scores closest to the minimum score. And when that happens, that's another way of saying positively skewed. Okay, now when it's positively skewed, as I just said, the mean is greater than the median. So what happens is all of these scores up here, even though they're less frequent, they're a long way from the median. So they actually, so if you think of the mean and median as starting off as equal, these scores up here drag up the mean. That's why it's more than the median. The opposite happens for negatively skewed data. So instead of having heaps of scores or scores with a high frequency closest to the minimum, we have scores with highest frequency closest to the maximum. It doesn't matter if the mode is not the maximum score as it is in this histogram. We can still see that the bars are much, much taller when scores get higher, and that's what negatively skewed means. As I said before, that means that the mean is less than the median, so the opposite has happened to positively skewed. So these scores down here have actually dragged down the mean, which is why it's less than the median. So if the data is not positively skewed or negatively skewed, it's symmetrical. So I'll draw a symmetrical histogram. Now, it's important to note it doesn't have to be perfectly symmetrical. So if I draw something like this, it's not going to be perfectly symmetrical, but it's close enough. Here, the mean and median might not be exactly equal, but they'll be very close. So something like this is symmetrical, in other words, not skewed. So the highest frequency scores are not clustered around the minimum or the maximum, they are clustered around the middle. So that's how you tell from a histogram. Now we can also tell from a stem and leaf plot, because stem and leaf plots are basically histograms on their side. So I've just drawn a random stem and leaf plot here. Remember, a score like this represents, so 1 is in the stem, means 110, 4 units, so that represents the score 14. And this would represent, say, the score 28. So what we can see here is that the data is about symmetrical. There's more scores closest to the middle. There is one more score over here, but I'd still say that this was symmetrical. So if you were to turn this on its side, it would look closest to this kind of histogram. Okay, now I should point out, when of course you're looking at a histogram or stem and leaf plot and determining skewness, it's not an exact science. So you might be able to argue that it's symmetrical or say positively skewed, as long as you give a reason. And your reason should be based on the definitions I've just given. Is there a higher frequency of scores closer to the minimum, to the maximum, or the middle? Or you can use the definition I gave earlier on. Is the mean greater than the median, or less than the median, or equal to the median? Okay? So again, please pause and copy this down if you need it. We'll now look at grouped data. Okay, so when we're drawing a histogram or when we have any set of data, sometimes there's just such a huge range of data, it's much more helpful to group the data. So for example, let's say I took my class and I wanted to look at their scores in a test. So if I wanted to display this on a histogram, well, yeah, I could do that, but there might be a huge range of scores. Moreover, it's entirely possible that nobody in my class gets the same score. So if I had like 30 people in the class, I don't want to draw a different bar for each one of them, and I don't want to have to space out my x-axis, all the way from 0 to 100 or whatever. So it might be easiest if I group everyone together who got, within a range of scores. So what we have on the screen here, this is called a frequency table. And I've just made up some data and I've put it into different classes. So each of these is a class. So instead of, treating somebody who got 63 different from someone who got 64, they're in the same class. So there was one person who scored between 50 and 59, 2 people between 60 and 69, etc. It's just a more convenient way to display and understand data. So I could turn that into what's called a grouped histogram. So rather than a different bar for each score, I give the bars based on a range of scores. So I don't need to start at 0. So of course, with any histogram, frequency is again on the y-axis and the score is on the x-axis. Okay, so for the first bar, I'm just going to label these 1, 2, 3, 4, by the way. So first bar only goes 1. Now the bar should be touching since it's a histogram. Second bar goes as high as 2. The next 2 go up to 4. And then the last one back down at 2. So the data's pretty symmetrical here. Okay, so what I do is I just put the end point of it. So 50, 60, 70, 80, 90. So the class interval should be the same for all of these, and it is 50 to 59. That includes a total of 10 scores. Class interval is 59 minus 50, which is 9. So I don't want to have, one bar representing 0 to 60 and the next bar representing 60 to 65, because that'll be misleading. The histogram won't be of any use then. So each of these bars represents the same range of scores, a range of 9. Okay, so that's what it looks like. Now, we can't actually figure out from this what the exact mean, median, or mode are. The reason is we don't have the raw data, but there are ways we can get around it. So we can find the modal class. That's easy as it's just the class with the highest frequency. So in this case, there are two classes, and the modal classes are 70 to 79 and 80 to 89. Now remember, any set of data can have more than one mode. If it has one mode, it's unimodal. If it has two modes, we call it bimodal, and more than that, we call it multimodal. Remember, if every score is the same, like every score only occurs once, we say it has no mode. So here, this data is like bimodal. Two classes have the same frequency and they're the highest frequency. Now, to find the median class, what we do is we find the class in which the middle score lies. So for the middle or the median score, you can use this formula. So let n be the number of scores. So if you use this quick formula, n plus 1 on 2, that doesn't tell you what the middle score is, what the median is, but it tells you the score that is the middle. So in my data here, I have 1, 3, 7, 11, 13 scores. So if I put it into this formula, 13 is n because there are 13 scores, plus 1 divided by 2 equals 7. The median is not 7. The median is the 7th score. It doesn't matter whether I consider it the 7th highest or 7th lowest. So if I look at my frequency table, the first score is 50 to 59, and then the second and third scores are 60 to 69, and then the fourth, fifth, sixth, and seventh scores are in this class. So the median class is 70 to 79, because the middle score, I don't know exactly what it is, but the middle score I know will be in this class. Now, we can estimate the mean as well. So this is actually a very long process. Again, we can't find it exactly. So to estimate the mean, what we essentially do is pretend that each score inside a given class is equal to the middle of that class. So what we're essentially doing is pretending that the score from 50 to 59 is exactly halfway between them, 50 plus 59 over 2. We're pretending every score in this class was equal to 64.5 and then 74.5 and so on. So what we do, same way we do when we're figuring out the mean if we have raw data, we go 1 times that, plus 2 times that, plus 4 times that, plus 4 times that, plus 2 times that. We add them up, that's the sum of scores, and then we divide by how many there are. So here there were 13 scores. So go 1 times 54.5 plus 2 times 64.5 and so on, get our answer, divide by 13. And that is an estimate of the mean, not the actual mean. All right, the last thing I need to go through with statistics is comparing data sets. Okay, so let's say I've got some data like this. So let's say test scores. Doesn't even matter what it is. So what we want to do is compare a numerical variable over a categorical variable. So here the categorical variable is gender, boys or girls. That's a category. So you ask someone their gender, they shouldn't respond with a number. I know we get a bit crazy in 2017, but they won't tell you a number. So that variable is categorical. Now I said the numbers represent test scores. So test scores are numerical. You ask someone what they got in a test, they will tell you a number. So we want to compare two different categories, the numerical data of two different categories. So what we can do for that, we might use a back-to-back stem and leaf plot. So it's very similar to a normal stem and leaf plot. You still have the stem. The stem is essentially, the number of tens. So here I'm going to start at 6 and go up all the way to 9. So you just put each category, one on the left and one on the right, and you do it exactly the same way as a normal stem and leaf plot you did in Year 7. So for this score here, 69 for girls, I just put a 9 there. And then there's 70, 72, and 74. The data needs to be in order from smallest to largest. And I can do the same with the boys. So no scores in the 60s, but 76 was the smallest, then 78, 80, 83, and 92. Okay, so this is a way to compare two data sets. Now there are some sophisticated statistical techniques that you can use to compare two data sets. We're not going to do that. All we're going to do is like draw a back-to-back stem and leaf plot and discuss whether the mean, median, or mode is higher for one of the categories than the other. Now, you can use Excel again to help you with these calculations. I just want you to make sure you can do that before the test. So, if we were to look at, say, the median of this, the median for boys is this score here. It's not 0 for boys. The median equals 80, okay? And for girls, again, there's 5 scores, so the median will be the third score. 5 plus 1 on 2 gives you 3, so it'll be the third score, which is 72, okay? So the boys have a much higher median, okay? Both of them don't have a mode. The mode's really not that helpful in comparing data sets. So you really only use it if you're asked for it, you know, because it doesn't say much. I mean, you know, we could have had a data set where 10 people for girls scored 80 and, 10 people of boys scored, 70 or whatever, but that doesn't suggest how the whole class went. Okay, so let's look at the mean. So we can calculate the mean for both boys and girls. Again, make sure you know how to do this on Excel. So for the boys, the mean is 409 over 5, which is 81.8. And the mean for the girls was 369 over 5, which is 73.8. So from this data set, the way we displayed it, it looks like boys did better. The statistics back it up. Boys have a higher mean and a higher median. So therefore, we might conclude that boys did better. We just want to have some evidence to back it up. We don't want to just look at it and say, oh yeah, it looks like boys did better. We want to find some statistics to back up what we're saying. And the fact that the boys have a higher mean and median does back that up. So if you're asked a question like that, you might then say, okay, therefore boys did better. Great. So that's all for statistics. Now we have to go through probability, so pause and copy this down if you need. Okay, so make sure you know the basics of probability. So you should know by now that the probability of any event is always between and including 1, right? So you can never have the probability of an event, being 2. If I say, what's the probability this happens, you need to give a number between 0 and 1, percentage, decimal, fraction. Anyway, it doesn't matter. As long as the number is between 0 and 1, you've done something right. So we talk about the complements of an event. So PE means probability of an event. So if I put a dash there, or I might put a line over the E, that means not. So this is the probability that the event does not occur. So it's common sense. Probabilities add to 1 in exactly the same way that percentages add to 100%, because 1 actually is 100%. So the probability, if I know the probability of an event, the probability that it doesn't happen is 1 minus the probability it does happen. So if the probability that you pass the test is 0.8, the probability you don't pass the test is 0.2, because they have to add up to 1. So make sure you know the basics of that. There is the golden formula for probability. It's like the central dogma of probability. The probability of an event equals NE, the number of ways the event can occur, over NS, the total number of events in the sample space. Or another way of saying this, the probability an event occurs is the number of ways it can occur over the total number of outcomes. We use this all the time, probably without knowing it. For example, if you roll a die, the probability you get a 6 is 1 over 6, because there's 1 6 on the die, 6 outcomes in total. What's the probability you'd get an even number? There are 3 even numbers on the die, so you can get a 2, a 4, or a 6. There are 6 outcomes in total, so the probability of an even number is 3/6 or a half. If you're giving the answer as a fraction, make sure you simplify it, and your calculator can do that for you, okay? So now we'll look at two-way tables and Venn diagrams. So let's look at this situation here. In a school of 300 students, 180 have blue eyes, 120 have blonde hair, and 70 have neither. And yes, I'm aware that 180 plus 120 plus 70 is more than 300, but that doesn't matter. So this is the kind of situation where we might represent information in a Venn diagram or a two-way table. They both do essentially the same thing. So we have two categories here, two categorical variables. Eye colour, specifically do they have blue eyes or don't have blue eyes. The second category is hair colour. Do they have blonde hair or not blonde hair. So we can represent the number in each category in a two-way table or Venn diagram. It's just a convenient way to represent information so we can answer probability questions. So firstly, we'll look at a two-way table. It's actually a 4x4 table. We call it two-way because one way we have information about one category. So we have set A and not A, and the other way we have set B and not B. So A and B are just sets. It could be the set of all even numbers less than 20, the set of all Myra students, whatever. Okay, it's just a collection of objects. Each of the objects in the set we call an element. So we want to display how many elements are in each set. So obviously for this two-way table, we want either A or B to represent blue eyes, the other to represent blonde hair. So I'm just going to represent A with blue eyes and B with blonde hair. Okay, I know I'm not very creative, that's why I'm a maths teacher. So we're just going to display how many are in each category in this two-way table. So we're particularly interested in these 4 numbers that go in these 4 cells, okay? Because there are 4 possibilities when you have 2 categories. An element can be in A and B, it can be in both sets, it can be in A but not B, it can be in B but not A, or it can be in neither of them. And those 4 possibilities correspond to the 4 numbers here. So for two-way tables, we usually also have a row for the total just to help us out. So again, the point of this is just to display information to make it nice and easy to answer probability questions. So we were told in the question up there, in the situation, there are 300 students in total. So that goes down here, 300 in total. Okay, so 180 have blue eyes. So I'm going to put 180 down here. So these 2 numbers here need to add to 180 because there's 180 with blue eyes. Similarly, 120 have blonde hair. And 70 have neither blue eyes nor blonde hair. That actually goes there. Okay, now it turns out we have all that we need to finish off the two-way table. We only need 4 numbers. So I'm going to write, so the ones I wrote in black are ones that were given to us, and the ones I write in green are ones we can infer. So, of course, if there are 120 students with blonde hair, there are 180 without blonde hair. 70 of those did not have blue eyes, so 110 must have had blue eyes, because 110 plus 170 is 180. So this number plus this number need to add to 180, so this number must be 70, and then 50 must go there, so that they add up. So 50 plus 70, of course, gives 120. I've now displayed the information in a two-way table. Now, I could have just as easily used a Venn diagram, okay? So Venn diagrams always look like this, 2 overlapping circles. Won't give you any Venn diagrams with more than 2. So one set's A, one set is B. So there are 4 numbers that go on the Venn diagram. They correspond to the 4 numbers in the two-way table that I highlighted for you, these 4 numbers that we're particularly interested in. Okay, the 4th one goes out here. So this here is, so this first box that I'll colour in green, that represents all of the elements in A but not B. This is all the elements that are in both. The next one is the number of elements in B but not A, and then the last one in neither B nor A. So there are 4 possibilities. So the first number on the left-hand side of the Venn diagram, that is all the elements that are in A but not B. And that's that number there. That's A but not B. Okay, so there are 110 of those. There are 110 people with blue eyes who don't have blonde hair. So there were 70 who had both. Then the next cell is B but not A, so they had blonde hair but not blue eyes. There were 50 of those, and then there were 70 who had neither. And all of these four numbers should add up to the total number, in this case of students, 300. And they do, which means we've done something right. So either the Venn diagram or the two-way table is a great way to represent the information. So if I picked a student at random, what is the probability they have, so A means blue eyes and they have blonde hair as well. So probability of A and B, or if we're using set notation, it would look like this, okay? So number of ways it can occur over total number of outcomes. I can pick 70 from 70 people that have both blonde hair and blue eyes, and there are 300 in total. And I can simplify that. Okay, what is the probability that they have blue eyes and they do not have blonde hair? Okay, so blue eyes but not blonde hair means they're in A but they're not in B. We look here, or we look here, gives us the same information. There are 110 to choose from out of 300 in total. So that's 11 over 30. Now the probability of A or B, so they have blonde hair or blue eyes, and in set notation that's A union B, we have to include all those that have blue eyes, all those that have blonde hair, and all those that have blue eyes and blonde hair. So in the Venn diagram, we're including everything inside the circle. In the two-way table, we're including this cell, and this cell, because all people in those cells either have blue eyes, have blonde hair, or both. And when we say or in probability, we mean or both. It's an inclusive or. So 110 plus 70 plus 50 is 230. So there are 230 people that either have blonde hair, blue eyes, or both. And it's 230 out of 300, and again, we can simplify that. Okay, so this has just made it a lot easier to answer probability questions, the two-way table and the Venn diagram. So now we'll look at tree diagrams, which are a little different. So tree diagrams help us with probability, and they help us determine the probability of multi-stage events. So unlike two-way tables and Venn diagrams, which display the number of elements in a set, tree diagram helps us list outcomes of an experiment, and we're talking about multi-stage experiments. So it could be, you toss a coin and then you roll a die. So there's two stages there. You toss two coins. There are two stages, first toss, second toss, and so on. So the tree diagrams are all about listing outcomes. So let's say, for example, we'll start with an easier one. I'll toss 3 coins. So each column of the tree diagram is a stage. So there's the first time I toss the coin, the second time I toss the coin, and the third time I toss the coin. Okay, so the first time I toss the coin, I can obviously get heads or tails. I'll just write H or T. Second time, I could get heads or tails. And the third time I toss the coin, I could get heads or tails. Okay, so it turns out there are actually 8 possibilities if I toss 2 coins. And the tree diagram helps me list all those. So to list the outcomes, I follow the path. So for the first outcome, it's head, head, head. Oh, I got all 3 heads. Then the next one, head, then tails. Okay? And so on. So I'll just go through and write all of the 8 outcomes. Again, that was the whole point of the tree diagrams, helping me list the outcomes. I just need to follow the paths, okay? And I should end up with 8 outcomes, okay? So this one was particularly easy because events are equally likely. Each time you toss a coin, heads and tails is equally likely. All of these 8 outcomes is therefore equally likely. Tail, tail, tail is exactly the same chance of occurring as head, head, tails. Okay, so all of these has a probability of occurring of 1/8. The probability of getting heads, heads, heads is 1/8 because there are 8 outcomes. One of them was head, head, heads. The probability of getting tails, tails, head is 1/8. Now, if I said, what is the probability that I get 2 heads, I'm not saying that it has to be head, head, tails. It could also be head, tails, head, or tails, head, head. So the probability I get 2 heads, there are 3 ways it can occur that I've circled out of 8 in total. So the probability that I get, let's say, no more than 1 head, so of course no more than 1 does include 1, so I just go through and look at my outcomes. So this has no more than 1 head, so does this, so does this, and so does this. So there are 4 ways it can occur, 4 out of 8 or a half, okay? So this is an example of a tree diagram with replacement. So you might be thinking, well, what are we actually replacing? Well, each time we toss the coin, if we get, say, heads, we replace the heads. You can get a heads the next time around, okay? That's what I mean by with replacement. I mean that the probability that you get a heads is the same at each stage. The probability you get a tails is the same at each stage. So that's what happens with replacement. We'll now look at one without replacement, where the probability isn't the same. So let's look at this question here. I need to pick 2 students for my maths teams. I can choose from Daniel and Liam, who are boys, or Jessica, and I want to find the probability that both people I pick are boys. So this is a multi-stage event because I'm picking a student and then I'm picking another student. So there are 2 stages to it. So this one is going to be without replacement, because once I picked somebody for the team, I can't really pick them again. I can't clone them. So this time, I won't have the same chance of getting an outcome at each stage. So I don't have the same chance of picking Daniel on the first go as I do picking Daniel on the second go. So we'll still do our tree diagram like normal. So there are 2 stages, so there will be 2 columns that I line up. So for the first stage, I have 3 possibilities. At first, I can pick Daniel, I can pick Liam, or I can pick Jessica, okay? So then, for the second go, if I've already picked Daniel, only Liam and Jessica are left. If I've already picked Liam, only Daniel and Jessica are left. And if I picked Jessica already, then only Daniel and Liam are left. So I'm still going to write the outcomes here. So we should be able to see that there are 1, 2, 3, 4, 5, 6 outcomes. So the first outcome is Daniel, then Liam, or I can pick Daniel, then Jessica, Liam, then Daniel, Liam, then Jessica, Jessica, then Daniel, Jessica, then Liam. They are the 6 outcomes. Now here, all of these 6 outcomes are equally likely, okay? It was just that, if I'd picked Daniel first, I have a 1 in 3 chance of picking him, but if I've already picked him on the second go, I can't pick him. That's why this is without replacement. It doesn't mean that these 6 outcomes are not equally likely. Okay, so they are all equally likely. So there are 6 outcomes. 1, 2 of them have both boys, Liam and Daniel. So the probability to answer that question is just 2 over 6, or 1/3. Now that question became so much easier after we did the tree diagram to list all the outcomes. Now, there are circumstances we use tree diagrams when each outcome is not equally likely at each stage. So for example, we might have a situation where it's not the same chance of picking Daniel as Liam. We might have, more of a chance of picking Daniel or whatever. Maybe he's a star student. Anyway, the point is that when we do that, you might see probabilities written on tree diagrams like this, for example. But we're not going to go into them. So for all the tree diagrams we're doing for the test, all the outcomes here should be equally likely. And you'll be able to use this to calculate probabilities. All right, I'm just going to come up with one slide of a summary of everything you need to know. So make sure you know everything on this slide here. So when I say mean, median, mode and range using Excel for the statistics component, you need to be able to input a set of data and program Excel to calculate the mean of that data, to calculate the median, mode and range of that data. You also need to be able to do a very simple chart in Excel, but the instructions will be given to you on the sheet. You won't have your own notes though of how to calculate mean, median and mode. So you need to know the difference between positively skewed, negatively skewed and symmetrical. You need to be able to look and a histogram or stem and leaf plot and determine, or at least make an argument about whether it's skewed or not and whether it's positively or negatively skewed. For grouped data, you need to be able to interpret a frequency table and a grouped histogram and calculate, if asked, the modal class, which is easy, the median class, and the mean, estimate the mean using the frequency table or the histogram. You also need to be able to compare data. So we looked at back-to-back stem and leaf plots. You need to be able to construct one of them, then calculate mean, median, and mode, and make an argument that compares the data, like, which group of people completed something faster or performed better in a test or whatever. The easiest part of statistics is knowing unimodal if a data has one mode, bimodal if it has two modes, and multimodal if it has more than two modes. Of course, if each data point is different, then we say it has no mode. For probability, you need to know basic probability, like how to find the probability of a simple event, and things like complements, knowing that the probability an event doesn't happen is 1 minus the probability it does happen. You need to be able to use Venn diagrams and two-way tables to answer probability questions. You need to be comfortable with and or questions, like what's the probability this and this happens, or the probability that this or this happens. You need to be able to answer those. So you need to be able to do multi-stage events. You need to be able to draw your own tree diagrams, list all the possible outcomes, and then answer probability questions. You need to be able to do tree diagrams with replacement and without replacement. I went through that just then. Now, by compound events, I mean events where there's more than one likely outcome. So you need to be okay with answering a question like, if I roll a die, what's the probability I get at least 6 or at most 1? If I toss 3 coins, what's the probability I get at most 2 heads or no more than 1 head? That's what I mean by compound events. All right, if you have any questions, please let me know. Good luck studying. I hope you do awesome in the test. This has been the luckiest maths teacher in the world. Have a great day.